alkyl halides and elimination reactions. That is our topic for discussion today. Elimination reactions, they have very high synthetic value. Just like substitution reactions, we have seen nucleophilic substitution with alkyl halides. Elimination reactions, they can be used for introducing a pi bond into organic compounds. This is the synthetic value. That is, the elimination reactions, they introduce pi bonds into organic compounds. So they can be used for the synthesis of alkenes and alkynes. Alkenes are hydrocarbons, you know that. Alkenes and alkynes. So alkenes are hydrocarbons, they are containing one double bond, that is one pi bond, and alkynes are hydrocarbons containing two pi bonds, that is a triple bond. Correct. Hydrocarbons that contain 1 and 2 pi bonds, that is alkenes and alkynes here. So for the synthesis of these hydrocarbons, elimination reactions are very, very useful. Now, just like in the case of nucleophilic substitution reactions, where we have seen two mechanisms, that is SN2 and SN1 reactions we have seen. In the case of elimination reactions also, there are two mechanisms like this, that is E2 and E1. The first one is substitution nucleophilic bimolecular and substitution nucleophilic unimolecular. In the same way, E2 and E1, that is E2 is elimination bimolecular and elimination unimolecular. Correct. So now it will be very interesting to see. Now you are given a substrate alkyl halide and a reagent. Okay. Now whether this reaction, it will give you a substitution product or an elimination product, and if so what will be the mechanism? Now we have got four mechanisms here. Which mechanism it will follow? So out of the four possible mechanisms, what will be the nature of the mechanism here in a particular reaction? We will explore all these possibilities here. So now the general features of an elimination reaction, that is all elimination reactions involve loss of elements. That is, elements from the starting material and a new pi bond is formed. That is a basic characteristic of an elimination reaction, that is losing a hydrogen and a halide. Generally, we can say loss of elements from the starting materials and a pi bond formation. So this is the essential characteristic of an elimination reaction here. So now alkyl halides, they undergo elimination reactions with bases. That bases means the Bronsted-Lowry bases, we mean to say. Okay, now the HX, they are lost. So a reaction of this nature, let us see the basic characteristic of an elimination reaction here. Suppose we are having, see, this is the alkyl halide here. So this is the one hydrogen. Then we have carbon and X. Okay, now this is reacting with a base B. So this will give you a pi bond is introduced here. New pi bond is formed. Then alkene is formed here. That is alkyl halide. It is undergoing elimination reactions with a Bronsted-Lowry base here. So the HX, it is removed. So these are the things here. This elimination, that is, these things are removed and nothing comes inside here. Okay, so this is the basic nature of the elimination reaction here. Basic characteristics we can say, and plus we have the leaving group here, X minus here. Okay, now so let us see some examples here, how the reaction is proceeding. So say for example this case, that is, we use only bases, basically the base induced elimination. CH2 say Br. So this is an alkyl halide here. So this is reacting with a strong base OH minus. So we will be getting a RCH double bond CH2 plus rest of the compounds here. Okay, so this is the most common examples. They are base-induced elimination reactions, or base-induced elimination of hydrogen halides, we can say, from an alkyl halide. So alkyl halide, base-induced elimination of alkyl halides, we can say hydrogen halides here, hydrogen halides from an alkyl halide. So let us see one example. So basically, generally we are using removal of elements for HX. We use only bases. We will say, for example, say another compound here, CH3, say CH2. Then we have this compound here. Okay, so this is reacting with a strong base, just like potassium tertiary butoxide. Potassium, then we have tertiary butoxide. This is a strong base here. So this will be giving you, so minus HBr. It is lost here. That is the most common example. We can say the base-induced elimination of hydrogen halide from an alkyl halide. So this will give you a alkene here. So this is the alkene being formed here. Okay, now when we are having, say for example, another compound, if we take it here, say we have, say, hydrogen. Here we can say put chlorine here. Okay, so this is reacting with a base, say sodium ethoxide. We can say Na plus O minus, correct? Et, CH2, CH3. So this is sodium ethoxide here. So here it is elimination of HCl, the hydrogen halide, base induced one. So we are getting this one. Okay, this is the alkene here, alkene formation. A double bond, a pi bond, it is introduced here. That is, a base removes elements of an acid, or that is acid HBr or HCl, etc., etc. Okay, this is all base induced one. Therefore, what is this reaction called? Now let us see. There is a removal of a HCl, that is a hydrogen halide. Removal of the elements of hydrogen halide. It is called dehydrohalogenation reaction. Dehydrohalogenation. So this is a very important route for synthesis of alkenes, dehydrohalogenation reaction. Now most common method, it is for introducing a pi bond, correct, in an organic compound and preparing an alkene. Dehydrohalogenation reaction, it is an example of beta elimination. We can say this is an example of beta elimination or 1,2 elimination. It is also called 1,2 elimination because elimination taking place from adjacent carbon atoms here. That is, elements are removed from two adjacent atoms here. Dehydrohalogenation, it is an example of beta elimination because it involves the loss of elements from two adjacent atoms. Correct. Now the alpha carbon and beta carbon. Alpha carbon is the carbon to which the leaving group it is linked or bonded, and beta carbon, it is the adjacent carbon, alpha beta. So we don't say alpha beta elimination usually, we say only beta elimination, or we can say 1,2 elimination. Dehydrohalogenation, it is an example of a beta elimination, correct. Now here 4 bonds, usually 4 bonds are involved here. Either it is broken, 4 bonds are either broken, or 4 bonds are formed, correct. That is the beta elimination reaction. So beta carbon means alpha carbon and beta carbon. So here this is the alpha carbon. Here this is the bromine. It is linked to this carbon here. That is, the leaving group is bonded to this carbon. That is alpha carbon. And the adjacent carbon, it will be beta carbon. Here in this case only there is one beta carbon. So in certain compounds there can be more than one beta carbons here. Depending upon that, we will be getting different alkenes here. So Now, so how will you write this mechanism? See, in a simple way, elimination mechanism for, you know, so we have C, and we have a hydrogen here. This hydrogen proton, it is taken away. The base will attack this proton here, correct? So this is the beta carbon here. Then this is the alpha carbon, CX here. So usually what happens here? So this is the leaving group, and here, correct? So we have the base here. This base takes this proton here. This is the simple mechanism of the elimination reaction here. So this is the alpha and this is the beta carbon. So this is the beta elimination. Now here, the base B, it removes the proton here. Base B, it is removing the proton from the beta carbon atom. Correct? Then it will be forming a bond here. So what is the type of bond here? It will be HB plus. That is the bond being formed. Then X minus, that is the leaving group here. That is the electron pair. We can say in the CH bond, it forms the pi bond, new pi bond, it is formed. Okay, so what is the type of this thing? The more important product is this one. This is the new pi bond being formed here. Along with that, HB plus and X minus here. So the electron pair in the CH bond of the beta carbon atom here, beta CH bond, electron pair. So this forms the new pi bond here. Okay, now the the pi bond is formed between the alpha carbon and the beta carbon. Pi bond formed between alpha and beta carbons here. Correct. Now the electron pair in the CX bond, what happens to that? X is leaving. When X leaves, it takes away the electron pair along with that. Correct. That is a leaving group. So this is the simplest way we can represent an elimination reaction here. So these reactions usually take place only with the help of bases, strong bases we use here. So, just like the sodium hydroxide, then we can have this potassium hydroxide, then we can have potassium tertiary butoxide. All these kind of bases are being used here. Then we can have sodium NaO, Ca3, alkoxides here, correct? NaO, CO, so many bases. We can use all these kind of bases for elimination reactions. And basically, these are all negatively charged. Negatively charged bases are used for, most common bases are negatively charged. So oxygen compounds. Negatively charged oxygen compounds like OH minus, OR minus. These are the most common one. Okay. For this elimination reactions to take place, the most common bases being used, they are negatively charged oxygen compounds like OH minus and OR minus here. Okay. Now, we can say, then how will you draw this? Any product, dehydrohalogenation, first you should locate the alpha carbon. Alpha carbon is the carbon atom. It is bonded to the leaving group. Okay. So for writing the dehydrohalogenation reaction, first locate the alpha carbon. Which is alpha carbon? Alpha carbon is the carbon to which the leaving group is bonded here. Then we have to identify the beta carbon. In certain cases, there will be only one beta carbon. Then there will be many beta carbons. So we have to identify all the beta carbons. That is the carbon atoms with hydrogen atoms here, adjacent here. Correct. Then we have to remove the H and X from alpha and beta carbons, and it will be forming a pi bond. Correct. So this is the way the elimination reaction takes place here. Now, for example, let us see, I will just show you one or two examples here. It will be very clear for you. Okay. Now, so we can identify a compound of this nature, 2-bromo, 2-methyl propane. Let us see what it is. So 2-bromo, 2-methyl propane. So this is our propane here. This is our propane skeleton. So this is 2-bromo. So this is 2-methyl. Okay. 2-bromo-2-methyl propane here. So identify the alpha carbon, identify the beta carbon. So here we have how many alpha carbons are here? All this is the alpha carbon. Alpha carbon is only one. 2 with the leaving group is bonded here. Now beta carbons. So this is the beta carbon here. There is another beta carbon here. There is another beta carbon here. So you can say it's a beta 1, say beta 2, beta 3, and all these kind of thing. Different kinds of beta carbons here. But these beta carbons are all identical beta carbons here. All beta carbons are identical. 3 beta carbons we can identify here, all are identical. Therefore, on elimination, we get only one kind of alkene. Correct? So this is the only type of alkene, only one type of alkane. In the case of 2-bromo-2-methyl propane, so when we are reacting with, say, sodium hydroxide or potassium hydroxide, we get only one type of alkene here. Correct? So all identical beta carbons are there, only one alkene is formed upon elimination of what is getting eliminated here, minus HBr. Okay, when HBr is getting eliminated here. Now, in the case of another compound, let us see the 2-bromobutane. What will be the nature? 2-bromobutane. So write the, how many beta carbons will be there? 2-bromobutane. So we have, this is our alpha carbon here, no doubt on that. So this is another beta. This is beta 1, we can say. So this is beta 2. Correct? So here we can say that in the case of 2-bromobutane here, there is one beta 1 and beta 2, two different types. Okay, two different beta carbons are there. But in the case of 2-bromo-2-methyl propane, we have seen only one alkene is formed upon elimination because all the beta carbons are identical there. Even though I have written beta 1, beta 2, beta 3, etc., but they are all beta carbons only. They are all identical one. Unlike in the case of 2-bromobutane here. Here beta 1 and beta 2, they are two different kind of beta carbons here. Two different beta carbons, beta 1 and beta 2. Therefore, elimination, it will give you two different types of alkenes. Okay, now there is a possibility of an elimination. We can say from the beta carbon, alpha beta 1, there can be an elimination, we will get an alkene, and alpha beta 2, there can be an elimination here. So there will be different types of alkenes here. Therefore, they are constitutional isomers, structurally different ones, structural isomers. So elimination will give you two constitutional isomers by the loss of HBr here. Okay, so alpha and beta 1 carbons or the alpha and beta 2 carbons. We can say using in the case of a base here, say one base, we can say potassium tertiary butoxide. If we use that as a base here, so we can have say CH2 double bond CH, CH2 CH3. This is one kind of an alkene, alkene 1 here. Okay, then we can have CH3, then CH double bond CH, CH3. So this is alkene 2 here. Two different types of alkenes are formed here. That is, first one is CH2 double bond CH, CH2 CH3, and other one is CH3 CH double bond CH CH3. The first alkene, it is formed actually, the first C, it is a beta 1 alpha. That elimination here, the alpha beta 1 carbons, elimination can take place here. And in the second case, second alkene, this is the elimination is taking place from alpha and beta 2, that is beta 2 carbon here. So different types of alkenes, two different types of alkenes can be formed here. So which will predominate? We will examine later. There are certain specific rules for all these kind of thing, So which is the predominant alkene? We will find out. Okay, now the mechanism we can see. E2 mechanism. Yeah, just like SN2 mechanism, because these things are all more or less similar. There are so many characteristics common to SN2, then E2, SN1, E1, and all these kind of things. So it will be very easy to understand here. Mechanism of elimination. So we know that in the case of nucleophilic substitution reactions, we have seen that there are two activities involved in any chemical reaction. Bond breaking, that is, certain bonds are broken and certain bonds are formed. Breaking of bonds and formation of new bonds. Now, mechanism depends upon the timing of the activities. That is, whether these two activities take place simultaneously, that is the cleavage of the bond and formation of the new bond, whether these two activities take place simultaneously. That is one point. Depending upon that, we have seen the mechanism is SN2. Correct. Therefore, that is a two, is a concerted reaction there. Correct. Therefore, in the same way, we can say elimination reaction. Elimination and this thing. In the case of SN1, we have seen actually there is a two-step mechanism here. SN1 reaction, unimolecular reaction, that is a bond breaking take place first and followed by bond making. There is an intermediate carbocation is formed, and all these things we have discussed earlier. Now we will see the E2 mechanism, that is a bimolecular mechanism again. E2, E1, just like SN2, SN1. SN1 is substitution nucleophilic bimolecular, and other one is substitution nucleophilic unimolecular. In the same way, E2 and E1. E2 means bimolecular elimination. E2, it is bimolecular elimination. And E1, it is unimolecular elimination. There are two mechanisms we can identify for the elimination reaction, E2 and E1 mechanism. So the difference here is only in the timing. Okay, timing of the bond cleavage and timing of the bond formation here. Similar to SN2 and SN1 mechanisms here. So E2 and SN2, E1 and SN1 mechanisms. These reactions have so many common features. Okay, so now the E2 mechanism, it is the most common mechanism of elimination. Correct? That is elimination in the dehydrohalogenation reactions here. That is the most common mechanism is E2, not E1. E1 is not that useful. We will discuss that. Okay. So for dehydrohalogenation, the most common mechanism is E2 here. So we have seen the kinetics here. Now in this case of a reaction of, we have seen that example, propane example, CH3 say C. Here CH3, Br, 2-bromo-2-methyl propane we have seen. So this is reacting with a base here. So we will be getting an alkene here. This alkene is formed here. Correct. So this is actually the kinetic. It is a second order kinetics here. This is the E2 mechanism. We are discussing E2 mechanism. E2 mechanism means it is the kinetics is second order kinetics. Therefore, what is meant by second order kinetics? The rate of the reaction. It is actually equal to K. That is the rate constant into, now we have the concentration of the alkyl halide. This is the alkyl halide, CH3. And the base. Okay, so this is the rate. That is second order kinetics bimolecular concerted reaction. All bonds are broken and formed in a single step. It's a single step reaction here. E2, it is a single step one. Single step. That is second order kinetics. Important point here. Okay. So E2 is the bimolecular, elimination bimolecular here. Second order kinetics, bimolecular reaction, rate depends upon the concentration of the alkyl halide and the base here. Single step, that is a concerted reaction here. Okay, now so how the reaction will be proceeding here? So it will be simple kind of a thing. You see, this is the bromine. This bromine is the leaving group here. So this is the beta carbon. So this is the beta carbon here. Correct? So we can just rewrite it here. This is the alpha carbon and beta carbon. I will just rewrite here so that it will be very clear for you. So CH3, then we have CBr. This is the alpha carbon here. Correct? Alpha carbon means the carbon 2 with the leaving group is bonded. Then we have the CH3 here, CH2. Then there is a hydrogen here, CH3 here. Okay, so this is the beta carbon and this is the alpha. This is alpha, this is beta here. So what happens here? So this will form the double bond here. So this bromine, it will go. That is the leaving group here. This is the mechanism here. Okay, now this base OH minus here, this will knock out this proton here. See, like this. So we will be getting the alkane here. Okay, the base OH minus, it removes the proton here from the beta carbon. Okay, always the beta carbon proton is removed here, and alpha carbon, the leaving group, it leaves along with the electron pair here. Base OH minus, it removes the proton from the beta carbon. Correct. Now the electron pair in the beta CH bond, okay, it forms the new pi bond here. Now the leaving group, it comes off with the electron pair in the carbon CBr bond here. Okay, so we can, in the case of a substitution reaction, we have drawn energy diagrams. In the same way, we can draw energy diagram for this reaction. That is, briefly, I will just tell you how this energy diagram can be drawn here. Something wrong here. X coordinate and Y coordinate we have drawn in the case of SN2 reactions here. This is a reaction coordinate. Roughly I will just show you. So in one coordinate we will be plotting the energy. Okay, this is the reaction coordinate. And here we will be plotting energy. Correct. For that particular reaction. Now the reaction proceeds here like this. Here you have the reactants. Like this. So we have here, this is the reactants here. We have seen that is CH3 tri-CBr. Plus the base here. Okay, so this is our energy of activation. Just like in the case of SN2 mechanism. So here, this is our product here. The product will be, so CH3 So is C double bond CH2, that is a alkene, plus we have water, then plus Br minus. Okay, so now this is the transition state here. Transition state, one step mechanism here. So there will be transition state will be having 4 atoms of the from the alkyl halide, 2 carbons, and we can say 1 leaving group and 1 hydrogen. Okay, so the transition state, how we can represent the transition state here? So we will have CH3. Okay, then we have C. So this side it is no problem here. So this bromine only, this bond, CBr bond is partially broken. Correct, there will be a delta minus, negative charge, partial negative charge will be here. Correct. Now this double bond, this is partially formed. This double bond is partially formed here. Okay, now the CH2 here. Then there will be a partial bond with this water, H. Then we have OH. Okay, there will be a partial negative charge here. So this is our transition state for this reaction. Correct? This is the transition state. CH3. So how many partial bonds are there? Partial bonds will be CH3, C, CH3, Br, CBr bond, that is partially formed, and C, CH2, that double bond, it is partially formed. Then CH, that bond is partially formed. Okay, then HOH, this is again, this is a partial bond here. This is not full bond, here is only partially formed. Like this, we'll have to show. Therefore, there will be 4 bonds partially formed. That is, 4 bonds are broken, 4 bonds are formed here. So 4 atoms from the starting alkyl halide there. Okay, now 2 carbon atoms are there. Then there is 1 leaving group and there is 1 hydrogen atom here. Okay, so this is the type of transition state here. Now the reaction, it is a one-step reaction. One-step mechanism, 1 transition state here and 1 energy barrier. Now 2 bonds are broken, that is CH bond is broken, and that CBr bond, 2 bonds are broken here, the 2 bonds are formed, that is HOH bond, and the new pi bond here, CH2, that pi bond, 2 bonds are formed here. So it's a single step reaction. E2, it is a single step mechanism. Okay, so the transition state, as I have explained, it contains 4 partial bonds with the negative charges there. This negative charge is distributed over the base and the leaving group. Okay, now if you see the entropy, what is entropy? Degree of, we have discussed it in my earlier class. What is entropy? That is disorder. The more the disorder, the reaction will favor a higher entropy, delta S. Okay, so here in the case of this reaction, the starting material, there are 2 molecules of starting materials here. Okay, so and how many molecules of products? 3 molecules of products here. So 2 molecules of starting materials form 3 molecules of products here. Therefore, the entropy favors the products formation. In this case, E2 reaction here. So the degree of disorder, or rather the degree of randomness, it is more here. Correct? Therefore, in the case of an E2 mechanism, entropy, it favors the formation of the products. Correct? Because 2 molecules of the starting material, it is forming 3 molecules of the products here. Correct? Now, let us see the factors. What are the factors affecting an E2 mechanism here? Just like in the case of an SN1 mechanism, we can identify so many factors. The first thing is the base. That is the factors affecting E2 mechanism. We can say first thing is the base one, because the rate equation contains the concentration of the base here. The rate equation, that is the rate is equal to K into the concentration of the alkyl halide and the concentration of the base there. Therefore, the identity of the base and the concentration of the base, most important points here, the base appears in the rate equation. Therefore, the rate of an E2 reaction, it increases as the strength of the base increases. Okay, now that is the base, because the base is here very, very important thing, because the base appears in the rate equation. The rate of the E2 reaction, it will increase, okay, depending upon the strength of the base. As the strength of the base increases, the rate of the E2 mechanism, E2 reaction increases here. So usually we are using strong, just like in the case of SN2 reaction, the strong negatively charged bases. That is OH minus, then we have this OR minus, and all these kind of things, these kind of bases are being used here. Okay, now that is a base. Now the other one is the leaving group. That is better leaving group. Better leaving groups, it will favor the E2 reactions here. Better leaving group, faster the E2 reaction. Now suppose we see better leaving groups means see RF. We have a compound here, then we have say RCl, RBr, then we have Ri. Okay, in the series here. Now this side, if you go from here like this, the leaving group ability increases. So from left to right here, the ability of the leaving group, like this, in this direction, increasing leaving group ability, it will increase the rate of the E2 reaction. Two arrows we can put here. First thing is leaving group ability. Then second one is the rate here. Okay, so the leaving group, better leaving groups, it will be the faster the E2 reaction here. So in the series of the alkyl halides here, increasing leaving group ability from fluorine to iodine, fluoride to iodide, when we go, the leaving group ability increases. Therefore, the rate of the E2 reaction increases from left to right like this here. Correct. And in the same way, solvent. We have seen the third point here, solvent. Solvent is, the polar aprotic solvents. Polar aprotic solvents increases the rate of an E2 reaction here, because polar aprotic solvents, say, which are the polar aprotic solvents like acetone and DMSO and all this kind of a thing, they do not solvate anions well. We have seen in the case of an SN2 mechanism here. So a negatively charged base, it is not hidden by by strong interactions with the solvent. Okay, therefore the base continues to be stronger. A stronger base increases the reaction rate. In the case of an E2 mechanism, a stronger base, it increases the rate of the reaction here. That is polar aprotic solvents. It will increase the rate of the E2 reaction. Why? Because polar aprotic solvents do not solvate anions. Correct? So negatively charged base is not hidden, rather by strong interactions with the solvent. Therefore, the base is a stronger base. Any strong base, correct, it will increase the reaction rate in the case of an SN2 mechanism here. Correct. Now, the fourth factor, that is the identity of the alkyl halide. There is a subtle difference here from the SN2 mechanism. Okay, identity of the alkyl halide. So that is the main difference between SN2 and E2 here. Now how the R group here, that is, it will affect the reaction rate here. So we have seen in the case of an SN2 mechanism, so increasing alkyl substitutions, it will decrease the rate of reaction. Correct? That is what we have seen in the case of an SN2 mechanism, increasing alkyl substitution. So as the number of the alkyl groups here on the carbon atom with the leaving group increases, the rate of the E2 reaction increases here. So we can say SN2 mechanism, what is the order of the SN2 mechanism here? That is, this is the SN2 mechanism, R, say CH2X. So this is the primary one. Then we have R2CHX, this is the secondary one. Then we have R3 CX. This is the tertiary one. Okay, now the SN2 reaction, the rate, here, it is in this order. As the alkyl substitution increases here, correct? As the number of R groups on the carbon atom with the leaving group increases, rate of the E2 mechanism, E2 reaction increases, unlike in the case of SN2 reaction here. Here it will be increasing rate of SN2 increasing. Correct. Now, in this order, elimination. This is the order here, increasing rate of E2 reaction, opposite trend here. Increasing rate of E2 reaction. Okay, therefore it is the opposite trend here. Correct. Opposite trend means the rate will be here. In the case of E2, R3, say CX, the rate is high compared to R2, CHX. Then we have R, CH2X. So this is the order. The trend here, the most important point, that is in the case of SN2 and E2 here, even though there are many characteristics similarities are there, but differences are also equally there here. Okay, as the number of carbon atoms or the number of R groups on the carbon atom with the leaving group, it increases, the rate of the E2 reaction increases. And in the case of SN2 mechanism, it is the other way around. That is, as the number of R groups on the carbon atom with the leaving group increases, rate of the SN2 reaction decreases. So the order will be reversed. That is, it is just like increasing rate of E2 mechanism, it will be in this order, and here it will be increasing SN2 reaction here. The trend is opposite. This is the major difference between E2 and SN2 here. Now, we have seen in the case of an alkyl halide containing different beta carbons. Okay, not similar beta carbons, there are two or more different beta carbons. So two different types of alkenes are formed, we have seen. So we have not examined which alkene it will be predominating there. So there is a rule for that. That rule is known as, it is ZAITSEV. It can be pronounced in different ways here. ZAITSEV. One way we can write here, or we can write here SA. Different textbooks we can see in different ways here, or SAYTZEFF. Okay, in different ways here. We have seen in different textbooks in this fashion, it is all written here. Okay, so this rule, there is a rule here, SAYTZEFF rule. We can say SAYTZEFF rule or ZAITSEV rule or so whatever it is there. So this will be helpful. This rule helps in forecasting, which alkene it will be predominating. Okay, in the dehydrogenation, okay, dehydrohalogenation of an alkyl halide having two or more different beta carbon atoms. Okay, it can yield a mixture of alkenes. That is dehydrohalogenation of an alkyl halide containing two or more different beta carbon atoms. Correct. It can yield a mixture of alkenes. So when this occurs, so one of the products, okay, one of these alkenes, it usually predominates. Okay, the major product, it is a more stable product. Correct. That is, which is in the case of an alkene, which is a more stable alkene, the alkene with the more substituted double bond. That is our ZAITSEV rule here. ZAITSEV rule or ZAITSEV rule. Here what is the major product in beta elimination? It has the more substituted double bond. That is a more stable double bond here. In the case of a dehydrohalogenation of an alkyl halide, okay, containing two or more different beta carbon atoms here. So when it can yield a mixture of products here, only one product will be predominating here. Usually one alkene predominates here. So which is the alkene which is predominating? That is the more stable product, more stable alkene. Which is the more stable alkene? The one with the more substituted double bond. So ZAITSEV rule says though, the major product in a beta elimination, it has the more substituted double bond here. So therefore, we can say this reaction, it is regioselective. This reaction is regioselective here. That means regioselective means what? It can yield, when the reaction can yield, predominantly or exclusively one or more constitutional isomers. Different types of isomers are there. Only one of the isomers, it will be predominating, or one of the isomer, it is possible. Correct. So E2 eliminations here, E2 mechanism, that is two different types of alkenes are formed or more. Correct. So E2 mechanism, it is a regioselective, because what happens here, the more substituted alkene predominates here. Different alkenes are possible. Okay, more than one alkene is possible here, because the number of beta, different two or more different different beta carbon atoms are there. Therefore, we can get it is called regioselective. We can get a mixture of alkenes here. It can yield predominantly, or we can say exclusively. Okay, exclusively only one constitutional isomer will be formed here. When a mixture is possible, that possibility is there. A mixture of isomers is possible, but when it is possible, there will be a predominantly or an exclusively only one product will be there. Okay. Okay, that is why the E2 reaction, it is known as regioselective, because the more substituted alkene predominates. That is our ZAITSEV rule here. The ZAITSEV rule results because the double bond, it is partially formed. Why it is happening? Because in the transition state here again. So in the transition state for the E2 mechanism, we have seen the double bond, it is partially formed in the transition state. Okay, now the increasing the stability of the double bond by adding the R groups. That is a more substituted double bond. That will be more stable one. The one double bond with a one double bond with a more substituted double bond, we can say that is a more stable one. So in the transition state, okay, the double bond is partially formed there in the transition state for the E2 mechanism. Therefore, now the stability of the transition state, so stability of the double bond by adding R groups there. So it will lower the energy of the transition state there. Correct. So lowering the energy of the transition state, therefore the reaction rate will increase. Okay. Lowering the energy of the transition state by addition of R groups there, more R groups. Therefore the the energy of the transition state, it will be lowered, so the reaction rate will be more there. Correct. So E2 elimination, now we have seen that compound. Let us examine that. We'll come back to that example, then it will be more clear. So E2 elimination of HBr from 2-bromo 2-methyl butane. Let us see a compound of this nature here, that is CH3 2-bromo, then we have 2-methyl CH3. Okay, this is our alpha carbon here. Then we have this is beta. This is also beta here. Okay, so we can say the beta 1. Different beta carbons are there here. So here there is another carbon here. This is beta 2. Correct. Beta 1, beta 2, and so many carbons are here. Okay, just for your understanding here. So in the case of this is a 2-bromo 2-methyl butane, we will get two different types of alkenes here in the reaction with a base. Okay, so let us see what are the types of products being formed here. So OH minus, that is the base here. Now first thing we can say the beta 1. Let us say beta 1 CH bond here. Beta 1 CH bond cleaving. Here that is the beta 1 CH bond, the cleavage. So what will be the nature of the transition state here? Let us see the transition state. That will be interesting here. So everything depends upon the transition state here. Okay, now let us see CH3, HC. Then we can have, okay, now here we have a bond. It is partially formed here, H. Then we have OH here. It's a partial bond again. Okay, then we have this double bond. It is partially formed here. Then we have C. Br, that is a partial negative charge here. Okay, so this transition state, it is forming here. This bond I have wrongly written here. It is getting broken here. Partially, it is getting broken. 4 partial bonds are there total. Okay, now it is clear. So we are having 4 partial bonds formation and breaking here. So this is our transition state here for this reaction beta CH bond cleavage here. Okay, so this will be a less stable transition state. So this will give you what will be the type of product here. So we will be getting, say, H. CH2, CH3 here. Okay, this will be the minor product here, because this is a disubstituted alkene here. So this transition state, it is a less stable TS. Less stable transition state. So this is giving a disubstituted alkene. Okay, as per the SAYTZEFF rule and all, we should get the maximum substitution. That is the most stable alkene here. Correct? So this is okay here. Now another one, we can say, this is one thing, the transition state. The second transition state, let us see how it will be. So what kind of alkene it will be giving here? That is the cleavage of beta 2 CH bond is cleaved here. Here this will be beta 1 CH bond. Now here it will be beta 2. So I think I will have to change here to avoid confusion. So this is the beta 1 CH bond here. Okay, that is the beta 1 CH bond cleavage. This transition state is there, and the second one, it will be beta 2. So the beta 2 transition state will be we will just draw here now like this way, so that it will be clear. Beta 2 CH bond cleavage. So what will be the nature of the transition state here? So CH3, then we have C, Br, negative charge here, correct? Then there will be a Ca3 over here, no problem. Then partial double bond is formed. Okay, now we have Ca3, then hydrogen, OH. So this is the transition state for the second kind of a reaction here. Okay, so this will be yielding. This is the most stable transition state here. So this most stable transition state, it will be yielding a tri-substituted olefin alkane. Correct. So this is A and this is B here. So B is the major product here because it is the more substituted double bond here. Major product, tri-substituted alkene is the major product and minor product is the di-substituted alkene here. Okay. So this is our rule. SAYTZEFF rule says here the more substituted double bond, it will predominate here. Okay. So this is the E2 elimination of HBr here. Two different types of alkenes are formed here. So one will be predominating here. Correct? Now, let us see some a mixture of what you call stereoisomer. It is possible. Correct? So from the dehydrohalogenation, the major product is a more stable stereoisomer again. Okay, everywhere it is the stability. The more stable product means that will be predominating here. Stereoisomers, that is different stereoisomers are possible means the more stable one. A mixture of stereoisomers it is possible. So from the dehydrohalogenation reaction, the major product, it will be the more stable stereoisomer. So for example, now dehydrohalogenation of say an alkyl halide. Okay, we will be getting a trans and cis alkenes are there. Then the trans alkene, that is the major product will be there. That will be the more stable one. Say for example, just we can say this C6H5 phenyl group here. Then we have C, H we can write here. H, the compound C, H, Br. Correct. So this is when we treated with say sodium alkoxide here. Correct. ET, that ethyl group here. Okay. So when this is treated with this thing, that is dehydrohalogenation reaction of this alkyl halide here. So this is our alkyl halide. Say this alkyl halide, say A. So this will be giving you two different types of products here. That is alkene, that is trans alkene and cis alkene here. Okay. Two types of alkenes will be there. So let us see which will be the pH is the phenyl group here. So this is the trans alkene. So this is the major product because major product is the more stable one. The trans alkenes are always more stable here. Now there we can have cis alkene also here. This is the cis alkene here. So trans alkene, it is the major product here. Therefore, we can say this is a stereoselective reaction here. Dehydrohalogenation, it is stereoselective reaction. When two or more stereoisomers are possible, so one is formed exclusively or rather predominantly, we can say. Okay, so E2 mechanism, it is stereoselective. Because why it is stereoselective reaction? So when two or more stereoisomers are possible, one, it is formed exclusively or predominantly over the other one. That is why this is known as stereo selective reaction here. So trans alkenes, they are more stable than cis alkenes because they are the steric interaction, because again the steric interaction here in this case the bulky phenyl groups here on the same side, that is a cis group here, therefore it is unstable. So trans alkenes are more stable than the cis alkenes here because they have few less steric hindrance here. Now increasing alkyl substitution, it will stabilize an alkene by electron donating inductive effect also. Okay, so these are the various points which we can discuss in this class. So next class we will be going in detail on the E1 mechanism and so many other allied aspects here. Okay, thank you so much for listening.